Now it is time to introduce our next speaker, Boris Trofimov, Big Data Competence Lead and Software Architect at Sigma Software. He has more than 17 years of experience in software development, architecting, team leading, and educating. Throughout years, he has successfully participated in tons of projects shaping big data architecture for companies in diverse industries. His portfolio goes from creating cost-efficient big data solution for innovative startups and getting them delivered in 2 weeks to designing of the advertisement data platform for the owner of the largest advertisement and video platforms with millions of users and billions of video plays. So please welcome. Hello, thank you very much for joining.
Hello, do you hear me?
Yes, loud and clear. So how are you doing today? Ready for the presentation?
Yes, definitely, yes, and thank you for such a pleasant introduction. I'm I'm very glad to join this amazing conference and have this opportunity to speak for you today. And my name is Boris Trofimov, and I'm Big Data Competence Lead. And actually, I'm ready to start.
Before we do, biology has been a topic
Sure.
in the conference. We
Yeah.
had another speaker with the background in an academical background in biology, and your topic of a presentation also combines the technology and biology together. Maybe a couple of words. So how did you come from big data to biology? Was it by accident? Was it some academical background as well?
In our lives there are always occasions which we can treat as like accidents, but I believe there is something more. And actually, by the way, the part of my presentation is about this, that not everything is coincident. So I came it from math background, so I had math background, my university, applied mathematics. I liked to learn Gödel's theorem, which will be mentioned in my presentation as well. And I came from there about limitations, what human body can and cannot. And then I slightly and seamlessly switched to biology and the way how it implemented on the material world.
That's an amazing way to start and to find the connections between the disciplines that might not be obviously connected, but in reality they are on the deeper level. So now the stage is all yours. So
Exactly.
please start the presentation whenever you're ready.
Yep, yep. Nice. I see my slide, the first slide. So yeah, today I would like to talk about quite outstanding topic, very unusual topic, I believe. It's nature and particularly human body as an infinite source of inspiration and design ideas for us software engineers. What we can borrow from nature, what nature can teach us, right, and or at least confirms that we are on the right way. So before we get to specific learnings, let me share a few examples of this beautiful connection between actually software we develop and software living in our heads. And let me start with the first example of protein build process or protein synthesis process, which suspiciously looks the same as executing regular software application. And this protein molecules is essential building material for our cells, for our body. Cells use it and produce it on a regular basis. So probably you're familiar with this classical architecture, like any informational system we use, develop. It consists of three blocks modules, CPU, hard drive, and random access memory. And I was thinking that humans invented it first, but looks like nature somehow was the first, in fact. And this separation, you will notice at the next example about protein building process, it actually will share the same design idea. So that's amazing coincidence. All right, so let's keep in mind the separation, and let me say a few words about DNA. I'm sure everybody's familiar with DNA, DNA molecules, and nature invented a very sophisticated way to store information on biological level in material world and 3D space. And DNA is a kind of that storage drive. It consists of, a lot of blueprints, for instance, instructions to create proteins. And nature had to invent how to organize this information. And nature invented notion of biological bit called nucleotide. Probably already know this from the classical course of biology, but let me recap it quickly. So it has four major values. right? And nature had to invent a biological byte called codon. Codon is just 3 sequential nucleotides in a row, which we can consider as biological byte. As you can see that maximal codon cardinality is 64 values, but only 20 values are connected with specific amino acids. The rest of them are reserved by nature for different things. And if you ever try to work and parse binary files, you might find a lot of similarities and parallels. All right, so DNA molecule is our hard drive, and it's very sophisticated file system. DNA contains files, pure files, indeed files, called genes. So every gene is a sequence of codons, and there are many different file types. There are programs in DNA to build different proteins. There are programs to build other objects, for instance, tRNA and others. Order matters, so sequence of codon define order of amino acids in a target protein. And yeah, there are magic bytes that which was reserved by nature. So magic bytes used to organize binary files inside DNA molecules. And among most prominent examples, promoter, which identifies start location of file, and actually stop codon, which determines the end of file. And probably you know that DNA is a double helix. It consists of 2 strands, and one strand is a template strand, they call it template, which is a source of truth. It consists of those blueprints or files. And the second one is a complementary and anti-parallel. It means that it's not the same as a template strand. However, it's in close connection. And if you damage any part of any of those 2 strands, it will be possible to recover the first part of strand based on the second one in any direction, which is amazingly. So it looks like nature invented kind of RAID array, biological RAID array. All right, so in order to execute our application, we have to load it into a memory. And nature invented kind of input-output processor called RNA polymerase, which knows how to build specific protein. So RNA polymerase, sorry, not protein, RNA polymerase. So RNA polymerase, it actually uses template strand, finds corresponding promoter, that magic on the template strand, melts DNA in that place, unzips and unravels strands, create a bubble, and start moving from left to right on a template strand. And what it does, it just copies codons one by one, sequentially, to the brand new object called mRNA, messenger RNA, which is a flash drive. Yes, we can call it flash drive. It will be a messenger which will transfer data to operating memory. So RNA polymerase moves this bubble, and what it does behind, it zips 2 strands again, unzips in front of and zips behind. And yeah, once RNA polymerase finds, we can treat it as a state machine in a certain sense. Once it finds stop codon, what it does, it just finalizes process, cuts mRNA, and mRNA is ready to be executed. On early stages, this copying process might be unstable because of different chemical issues. So it might be aborted at any time at the beginning. So what RNA polymerase does, it just retries. It makes several attempts to get to the moment when the copying process gets stable enough. And I'm a big data engineer, so for me, it's pretty natural to implement several retries for my ETL jobs. I'm using it on constant basis. It's a natural way to design jobs for big data, not only for big data. And anyway, good to know that nature didn't invent anything better than just retries. Yeah, so we have our flash drive, which, sorry, it's my youngest kid. Very sorry about it. So yeah, we have our flash drive with instructions, and we need to transfer it from nucleus to the cytoplasm, which is our operating memory or something like that. We can at least treat it like that. And nature invented another component called ribosome, which might be treated as a Turing machine, and this mRNA might be treated as a tape for Turing machine. So what ribosome does, it picks up this mRNA and start executing, actually translating those instructions. So first, it tries to start to find the actual point on a tape where instructions actually going to happen. So ribosome tries to find two another magics, cause a consensus sequence and stop codon. Right after stop codon, there will be instructions with information about amino acids. Well, technically, it's not instructions, it's identifiers, right? Every codon means specific amino acid ID, something like that. Remember those 20 values. So ribosome, it starts interpreting codon one by one and builds protein molecule. It just chains. You might ask where it takes from. Well, those building blocks, amino acids, are floating around, and they are delivered by tRNA, just another object. And ribosome knows how to communicate with tRNA and with chemical gravity or something like that. It just picks up the corresponding amino acid and changes it into the our current continuously building protein molecule. And when ribosome finds stop codon, it phenolizes protein. And protein, after that, is ready to be used by cell. Brilliant. Keep in mind that this mRNA as a flash drive can be reused several times. Nature does a lot of smart work, and we'll talk about it later, to save energy. And this is one of those activities. So these blueprints might be reused several times to synthesize different instances of the same protein molecule for a while. So let's keep this in our mind. All right. So another interesting topic is ChatGPT. I'm sure everybody knows about it. It would be totally disgraceful not to mention about it. It deserves to have a separate slide. Clearly, behind this hype, there have been countless attempts on simulating a human brain. And for a long time, it was a kind of cargo cult. We tried to build our neural networks, and they just didn't work as we expected, right? And we did it for decades. Scientists did it for decades without big luck. And only recently, they realized what has to be adjusted, what was wrong. In 2014, they invented generative adversarial networks, then transformers appeared, and finally, ChatGPT came to our lives. They realized importance of self-regressions, specific architecture decisions that have to be made between neurons. And finally, ChatGPT works really great. And I'm saying this for sake of honesty, because we borrowed concept of neural networks from nature, made it work, and the future might look scary or not scary. It depends. All right, so I'm saying this also because ChatGPT and this stuff brings up very interesting question. Are we computable beings? In other words, can we be replaced with a probably giant but still a computer, kind of Turing machine? And computable here means that there is algorithm behind it, which can be implemented by corresponding Turing machine. Our brain is a huge, perfectly designed biological neural network. It contains 90 billion. Thank you very much. It consists of 90 billion neurons in average. And most of scientists believe that our mathematical models of neurons and neural networks are pretty close to reality. Yeah, there are still some obstacles and vague things, maybe lack of understanding on the general picture, big parts of architecture and neurons. But in general, math models are pretty close to the reality. And there is an equivalence. There is a theorem which states that Turing machines with finite tape equal to neural networks, which means that for every neural network, we can build similar Turing machine with finite tape and vice versa. So it means that our brain and logical reasoning is computable if there is equivalence between them. You might say, and what? Well, in fact, there might be far-going consequences and implications depending on your belief. So one obvious implication is that if we are Turing machine, that our behavior is completely deterministic, and we behave, and there's no big difference between us and those robots from Western world TV show Netflix. Another implication is that our universe depends on specific laws and rules. Everybody knows it. And there is a famous and legendary Gödel theorem, which states that it makes hard limit on completeness of any theories that can be expressed with symbols in our universe. And in other words, regardless of language, regardless of logical reasoning approach, there are things in our universe that cannot be proved, fully proved, and fully described within the world by computable beings, by us. And if you believe in Laplace demon, the things might get even worse, because in this case, every new state of universe completely depends on previous state. Well, fortunately, most of scientists and people don't believe in Laplace demon. There are reasons behind it, but these arguments against free will are very, very scary. So there must be hope, and there are scientists who think different. For instance, famous Roger Penrose, very famous mathematician and physicist, a Nobel Prize winner, by the way, and they believe that the answer is in connection with quantum mechanics, this micro world. There is answer why we are not doomed in this case, so to speak. So scientists claim that we are non-computable beings. Yes, there are predefined programs in our heads. Yes, our brain is a giant Turing machine with a huge tape. However, there is another tape. There is another tape, secret tape, let's say, located somewhere in micro world, with where actually new instructions might came to us. Might come to us. So Penrose says that we are not closed. We're not closed system, and human bodies have kind of an interface with this micro world. And this interface is implemented by tiny subunits located in neurons called microtubules. So these microtubules are tiny enough to be able to behave as an observer, so register individual particles and quantum effects. So Roger Penrose says that, like, before decision is made, a universe might coexist in, so to speak, multiple states in parallel. And once choice is made, then that wave function will collapse, and microtubules will register, will observe new particles in certain sense, and this new signal will be registered, generated, used, propagated, and our brain will treat it as ours, something generated inside the system. So think about it, it's very interesting stuff. And by the way, Roger Penrose wrote a couple of interesting books explaining more his point, so I recommend reading them. All right, so enough speculations. Let's get back to learning itself. And the first learning is that nature follows domain-driven design rules. Let me explain why. So human body is a distributed system, very complex distributed system. It consists of many different parts. We call them organs, working together, and they going to meet the common goal: keep us alive, keep us conscious as long as possible, as much as possible. And every such organ, it takes some responsibility: unique internal structure, cells, multiple abstractions levels, input-output interfaces. Right? Every organ can receive commands and send events. And there are other organs, brain and spinal cord, which coordinate those organs and muscles. And what they do, they send commands to organ and receive events from them through neural network, which can be considered as the place where process managers or sagas live. So we can treat brain and spinal cord as a place where all those sagas controlling organs live. And spinal cord, by the way, beside acting as API gateway in certain sense, because it bridges interfaces, it amplifies signals, it does very, very important function. It contains those sagas which are responsible for most critical life processes, like organ control, where latency matter. And nature decides that it's more reliable to host those sagas closer to organs rather than keep them inside brain. So sending signals back and forth between brain and organ might be unacceptable. So data locality was introduced. like regional deployment, so to speak. So if you're familiar with Amazon Lambda Edge and geo distributed deployment, you definitely might find some parallels. So another important observation is that there are almost no horizontal connections between organs. Everything, every connection, every interaction, everything that we have, it comes through brain and spinal cord. That's very important. Those sagas control this interaction. So, in my opinion, nature follows domain-driven designs. And lessons, what kind of lessons we can learn? So, first of all, introduce functional bounded context. Still actual, still important. Wrap every bounded context into and break down it into the dedicated microservice or microservices that implement bound context domain specific language. Recursive breakdown. Clearly, we have rules on breaking down and decomposing microservices, solution into microservices, and the same rules might be applied recursively. So we need to zoom in our microservice, its boundaries, try to identify its component, its cells, so to speak. From domain-driven design perspective, what cells are, what they look like. It is our aggregates. Aggregates, kind of transactional context units, and we need to define commands, events that come and run through all those bounded contexts. So that's the similar idea, just another abstraction level. So use domain events. Use domain events about changed state of your aggregates, of your microservices, to decouple services even more. When Eric Evans, who's the author of Domain-Driven Design, he was asked what he could add to his famous book, what was missed from very beginning. He simply said that domain events, that was something that he didn't notice in time, and it wasn't included into the book. So domain events is definitely a very important thing. It must be used regardless of even domain-driven design. All right, so adaptivity and energy efficiency. You probably know that our body has outstanding energy efficient mechanism to regulate, for instance, temperature, body temperature. For instance, when it's cold, then vessels constrict, which reduces blood flow to the skin, and it minimizes heat losses, and vice versa. When it's really hot, sweating and vessels dilation, what it does, it helps get rid of extra heat. It's very practical reason behind it. And also human body, it uses very efficient way to store energy. It stores energy in the form of glycogen in the liver and muscles, and as well as, by the way, as body fat. Body fat is also a source of conservation, way to conserve some energy. And these energy storages can be mobilized when needed to ensure continuous energy supply by body. Energy recycling. The body efficiently recycles and reuses a lot of energy-rich molecules. For instance, those mRNAs. mRNA is pretty expensive molecule, so body tries to reuse it. And another example, during prolonged starvation, body can break down non-essential tissues and recycle their components and produce even more energy from that. So indeed, very outstanding mechanism to save energy and be adaptive. And lessons for us, first of all, definitely it's about utilization management and power management. So what we can use, like we can use clouds to simplify these decisions. We can use serverless, and I recommend considering serverless for sure, because it helps automate a lot of things like resource allocation, manage spikes in the throughput in many cases. I'm a big data engineer, so for me, for a long time, it was natural to build stateful clusters which would run my jobs, and the clusters would live for months. And they had to be tuned and configured very gracefully. Otherwise, it would be a disaster, a catastrophe. Nowadays, a lot of things get more easier, and my recent projects are like rely on serverless on all tiers. Even storage can be serverless nowadays as well, like for instance Snowflake. So there are examples which we can use, leverage, and To be honest, like serverless, indeed, it gives a great balance between costs, efforts, we apply as engineers, um, our comfort as an engineers to maintain and evolve it. So it's really good way. Of course, data compression and conservation. Probably here, the only one recommendation would be don't forget about different class storages. For instance, on S3, if we talk about Amazon, there are other alternatives for other clouds, but the idea is the same. Save money. If you have some data which is barely used, but you don't want to remove it, put it to the corresponding kind of deep archive or glacier. Put it there. It would save a lot of money. And always measure cost of change. For instance, on my project, we translate cost of allocated resources connected to some feature, every new feature, we translate them into the number of cups of coffee, so to speak. For instance, this new glue job will cost 1 cup of coffee per week or 4 cups of coffee per month. Yes, it's metaphor, but still it helps perceive costs, accept them, play with them, and for every new feature we strive to introduce, allocate least resources. That's pretty clear, but we measure it with a least number of cups of coffee for every new feature. And constantly monitor your bill, usage bill on the cloud or not only cloud. On daily basis, it's important to monitor it on daily basis, to check it on daily basis, because this is only one way to understand anomalies, patterns that you can reveal. Those insights are very important because the only one way to control it is to measure it on constant basis. That's how you can quickly understand why it's growing. Okay, so let's move on. The next topic is fault tolerance. Our body is designed to be very reliable and work for years. And at the end of the day, you probably know that we are the biggest enemies to our bodies, humans itself. So every organ is designed to be and to work very reliable and to work under very heavy conditions for years. There are examples like heart, liver, stomach. All of them have a lot of different levels of protection, like, for instance, partition tolerance, self-healing things, a lot of retries, and so on, mechanisms. There are examples of redundancy, for instance, lungs and kidneys. These are examples of redundant organs because it's important to find another parallel, right? And nature did it intentionally. So the body can continue functioning even if one instance, so to speak, fails, and it just spreads a lot across existing instances. So it's a very important way to achieve fault tolerance. And thought for us, informational redundancy. Every cell has own unique copy of DNA, which means that every cell can run that software, like executing blueprints, just in parallel, without any blockers. So clearly, it's a sign of informational redundancy and self-healing capabilities. They can detect and repair a lot of things automatically. For instance, like everybody knows what wound healing is, so it's about that for sure. Our body is able to develop immune response for unknown viruses. It's another wonderful example of self-healing. We just need to stop preventing our body to do this, probably in many cases. And efficient feedback loop. Again, we have a lot of sensors, and our body monitors everything. It can be body temperature or blood sugar, a lot of things, and all those metrics, telemetry, as collected by body and is analyzed, and body can escalate, and therefore keeps us alive and conscious as long as possible. Lessons for us. Okay, you can consider high availability options, and with clouds, it's a way easier to do it. For instance, multiple availability zones, load balancers, multiple instances, scale out, scale up. A lot of things exist. Worth thinking about data redundancy. By data redundancy here means that, again, following domain-driven design, you have to introduce dedicated storage per bounded context. It's very important to separate concerns by that and downside is that it's data redundancy, which might help if something goes wrong here, something will be good there, something like that. So don't afraid of data replication. If you need information from another bounded context, you can always subscribe to event from there and assemble state locally. So don't make direct calls. And automatic repair, we always should be thoughtful on the logic we implement, edge case scenarios and so on. Like somebody told me years ago that perfect application, perfect program is not when it works great on sunny day scenarios. Great program is great when it works on all edge cases. So for us, we just need to see task and just outline of possible edge cases for the specific either algorithm, procedure, function, whatever, object class. So from this perspective, we just need to think, keep in mind, it's kind of a checklist, right? Okay, I have network, so I have side effects. I need to think about what if connection will be stale, or what if there will be input-output outage somewhere in the beginning. So that's about it. And yes, introduce continuous monitoring. To be honest, high availability mode is very expensive thing, and I do believe that not every project needs high availability features. So for many cases, introducing reasonable monitoring on a project is more than enough to just be in touch with your deployed components and be aware in time if something goes wrong and escalate it in time. And in many cases, business accepts it and it's very good enough. CAP theorem. I'm sure that you probably heard of CAP theorem and its implication on informational systems. Briefly, for any informational distributed store system, it's impossible to achieve three qualities at the same time: consistency, availability, and partition tolerance. You can achieve only two of them in any combination over the third one, but not all together. And it sets kind of hard limits. There are reasonable ways to mitigate it in certain sense, some limitations and so on, but in general, this theorem sounds very reasonable. And if your human body is informational store system looks like so, then probably it should be applicable to us. And if that's true, what would be nature's choice in this case, right? Interesting. So let's address it one by one. So availability. We do know, aware of those examples with scale-up features, like several organs might be highly available, right? That's what I mean by organ redundancy. Kidneys, lungs, and so on. It's a clear example to keep us available. Again, low latency limitations on oxygen delivery to brain and any cells to our body. In fact, it is actually only 30 seconds, a very hard limit, and body does the best and tries to do the best to have a round trip of blood throughout the body within 30 seconds. Again, to deliver a lot of important peaks in time, regardless of temperature outside and so on, if it's cold or hot. And of course, if constraint is partially met, body still does the best to keep human alive. It can disable certain subsystem parts to keep human alive. Actually, here we mean that's what I mean by availability: being conscious, being alive. And of course, strong feedback system driven by monitoring, which we have. It's also essential argument for availability. Another, partition tolerance. It's possible to live with certain organ and peripheral disabilities, and you know those examples. It's a definitely example of partition tolerance. And every cell might have, actually has, copy of DNA, and a cell can regenerate a lot of things autonomously, thankfully to information redundancy, which is a sign of partition tolerance. Consistency. Well, DNA copies might be corrupted and cause different things like autoimmune disease, cancer, and so on. It's a downside of data redundancy, unfortunately. Signals that can be corrupted, they can be corrupted. throughout our body. It's a reality. It's a physical, material world. And in many cases, nature uses eventual consistency design ideas. So think for a while, what would be nature choice in this case? Which combination? This is in my guess. I think it is availability and partition tolerance over consistency. All right. Message driven. Nature had to invent a lot of different communication transport channels. It's pretty obvious to us. It has a lot of different priorities. Motivation is different priorities, SLAs, needs, types of data it is responsible for. So we have in basic, and that's what I'm going to focus today. It's a nervous system, circulatory system, and lymphatic system. There is another one, fourth one, less romantic, so we'll skip it for today. Okay, nervous system. So probably most complicated, most sophisticated informational system. It is responsible for controlling all life process, right? Blood pressure, body temperature. Fight or flight mode. It's a mode when body has to be collected as much as possible. Somebody calls this mode like run baby run, when it's very important. It's a question of life or death. So nervous system here plays crucial role. Of course, it's responsible for different communications. The data types here is commands and events, right? You remember that brain and spinal cord send commands to organs and receive events from them, and neural system is just a physical infrastructure level for this. And several communication channels to serve different SLAs. It would be naive to think that nervous system is just one giant network. In fact, it consists of different subsystems. Muscles and organs are controlled and isolated by several neurous networks, and the reason is separation of concerns. It's very important to separate crucial organs from just, for instance, working and playing with muscles, so to speak. So they just controlled by different neural subsystems, again, to separate concerns. If something wrong happened with the first subsystem, the second subsystem will be able to continue functioning without affection. And locality matters. Critical communication between internal organs and spinal cord. That data locality I mentioned several slides ago. It's another reason why nature tries to balance it, try to locate things closer to each other when it's possible. And you probably know that speed of signals is up to 100 meters per second, and length of neural fibers is 75 kilometers. Compare with blood vessels, like 100,000 kilometers. Another subsystem is circulatory system. It's very, very sophisticated. Another sophisticated system. It's rather transport rather than informational. It delivers oxygen, amino acids, sugar, hormones, water, a lot of liquid. So technically, circulatory system was invented and is a result of the fact that we live in the material world, and body depend on chemical reactions. Not everything, unfortunately, can be implemented with just informational neural signals. Not everything. There are chemical reactions which depend on oxygen, water, and so on. So body had to invent kind of unified transport tier to deliver a lot of things together, and the circulatory system is a response. It has strong SLA. Again, those 30 seconds must be met. That's why circulatory system has own pump. It's our heart, clearly. And the tremendous length of all blood vessels, 100,000 kilometers. It's insanely huge. And it explains why every cell is somehow connected and can receive those important vital things from blood. All right, lymphatic system. It serves two functions. The first one is responsible for having kind of biological laboratories in our body where little portions of new enemy viruses can be delivered, and the reason is to develop antibodies against these viruses. So it's transferred in dedicated rods, in dedicated system. Those how to say foreigners, unknown viruses to our body. And the second function is just canalization. It's garbage collection in many cases. So it helps cells get rid of biological rubbish. And there is no SLA comparing to the previous system. That's why it has low priority and low throughput. And there is no need in pump. That's why lymphatic system doesn't have own pump. All right, lessons for us. So consider message-driven design architecture, if applicable, of course. Nature proves it's extensible and scalable. Back pressure, think about back pressure from very beginning. Distinguish different types of data you have. Likely you'll have commands, events, maybe data messages, and there are different technologies, well-tailored frameworks to work with these kind of events. Yeah, all right. The last one for today, ladder of abstractions. Clearly, our body is a perfect example of ladder of abstractions, what it is. So our body is functioning on multiple tiers. There is an entity human body, which consists of different organs, systems. They consist of cells. Cells consist of molecules and so on. And every such tier, it has a certain level of responsibility, ownership, so to speak. It uses building blocks, building bricks from a downstream tier, helping implement own domain-specific language on this tier. Our body is indeed very complex, and that's why it's great evidence that it's possible to break down complexity in this way and spread into multiple tiers. And we are the best probably example of that. For us, it means that we should be very responsible and thoughtful for abstractions we introduce, their contracts, tiers our abstractions reside as well. Define architectural levels through abstractions tiers, not vice versa. That's important. And everything will be okay. So, yeah, message to you for today. Look around, learn from nature. Not just human body, the whole nature is a wonderful inspiration, source of inspiration, and it has beautiful and sophisticated design, technically polished with million years of evolution. So I'm done for today. Thank you very much. If you have any questions, time to ask.
Thank you very much for this presentation. It's actually very inspiring, and those parallels that you have shown between the way that nature designs things and that we are designing, like engineers, like we are designing our systems, they are indeed non-trivial, right? So they are on the surface, but it takes a little bit of time and skill, right, to spot these similarities. Keeping the time in mind, I will just ask one probably question, right? And that will be, but it's going to be a long one, right? So the way that nature usually designs things is it's kind of, nature is pretty agile, right? So it designs the simplest thing that could possibly work, the simplest probably strategy that could help this specific version of beings to survive in this specific ecosystem and in this specific conditions. It's not designed to like optimize things. We don't do the lasers from our eyes, although probably going to be kind of not bad to have, right? I wouldn't mind. And when we're talking about the software system, we are oftentimes trying to optimize further than the simplest thing that could possibly work. For example, when it comes to the cost optimization, you would not say, hey, we have 300,000 budget per month, so I have designed you the system that consumes 300,000 bucks per month because that's what you have, right? And this system will survive according to these rules. So do you think that our engineering approaches should be following this kind of a natural ways of evolving and looking first at the simplest things, or more on the structured and pre-designed approaches where you would plan for optimizations even beyond what is strictly necessary?
That's a good question and complex question indeed. Probably 40 years ago, it was Donald Knuth who mentioned that don't optimize in advance. And there is a certain actual truth behind it. There is a reason behind it. You, at the beginning of building something, you are not aware of all possible scenarios and cases, and it will be just either over-engineered solution, or you just waste some time and money. Maybe you would just have right guesses, but in many cases, guesses are wrong. So I'm voting and tending to the way of be simple from very beginning. Don't overcomplicate from very beginning. Use approach step by step. It's, so to speak, a comma razor or something like that. Introduce only necessary abstractions, and if you need to introduce more, you have a chance and opportunity to introduce and complicate it. And life shows that at this moment we see that, wow, these abstractions is a great, they can solve a lot of probably all cases, but in a 1 month or in 6 months you will find edge case where your abstraction is completely broken and you need to redesign it, refactor, and you justify why you need it, and customer says, come on, you did it 6 months ago, and you justify that it will be final refactoring, and you do it again and again. It's just like a matter of our life. So definitely simplify it, and I think the nature is a really good source and confirmation this approach works perfectly.
Thank you very much. That was indeed a very inspiring presentation, and as I said, many people here are finding these parallels more and more frequently between biology and natural world and the IT and systems and the design thinking aspect of things. So definitely a thing to look at in more details, to maybe find some additional sources of inspiration. We all need those sometimes. So thank you very much for presenting this.
Thank you. It was my pleasure. Have a great rest of your day. Thanks. Bye-bye.
Thank you.